our discussion of ratios. And we have two values assigned to elements of a population. The running example in the book would be, these would be the number of beds in hospital I. That would be XI, and these would be the number of discharges in January 1968. In hospital I. And that would be the number YI. So each pair XI, YI represent two distinct measurements of an individual I in some population. And again, the population parameters are mu x, mu y, sigma x squared, sigma y squared, sigma xy, and R and rho and by the way, another way to express R is as mu sub y over mu sub x. The reason being you can divide top and bottom by 1 over capital N and not change it. And then the numerator becomes mu sub y and the denominator becomes mu sub x. And I guess this is called the population correlation coefficient. All right, so the goal is to estimate R. I guess maybe there are two things that can be done. One is to estimate R. Oh, I forgot. There's also tau x, tau y, and, well, I'll leave it there. There's the population total, tau sub x, and there's the population total for the y, that's tau sub y. I've written enough. If it fills up that board, that's good. select n individuals from the population, capital X1, capital X2, capital X sub little n, and capital Y1, capital Y2 through capital Y little n will be there. I can't believe it. Over the weekend I was reading maybe late last week, I was reading a newspaper, and there in one of the newspapers from my home state, they wanted to use this word, this form of there, but they wrote T-H-E-R-E right on the front page. I thought, oh. Will be their X and Y measurements, X and Y values, respectively. And capital R equal to capital X bar over capital Y bar will be the estimate for little r. Another thing that's done, often the x values are known. And, oh, I'm sorry, I did it again. This is y bar over x bar. And the ratio estimate can be used to give an estimate of y bar, mu y. Sorry, mu x over. So here we take the known population mean. So for example, in the hospital example, the number of beds in the hospitals, you can get that information. It's not so hard. Number of discharges changes every month. It's kind of random. So you might know something like the number of beds in the hospital. But you want to have some estimate of how many people are being discharged from the hospital in a given month. You use this because there's some sort of positive relationship between number of beds and number of discharges. The more beds a hospital has, the more occupants those beds will have, the more people will be discharged. So there's some sort of positive correlation between the two. You might undersample somehow the number of discharges, and that would mean you're underestimating it. In other words, y bar might be an underestimate for the true mean number of discharges. And that would mean you're probably underestimating the mu x with the x bar. In other words, you select little n hospitals, and you find that the mean number of discharges is this. This might be an underestimate. If it's an underestimate of mu y, then this should be an underestimate of mu x, and that means this ratio here, mu x over x bar, should be bigger than 1, and that sort of corrects this. Multiplying this times that would then correct the estimate of y bar. Conversely, if you sort of were unlucky and selected little n hospitals and y bar was overestimating mu y, then x bar is probably overestimating mu x because they're positively correlated in some sense. And that would mean if this is bigger than that, that means this ratio is smaller than 1. And so you're going to multiply a number smaller than 1 times this overestimate. That should correct it back to a better estimate. So this estimate has for the for the mean in the y values has some advantages in some situations. And not only that, the standard error for this estimate can be better than the standard error for just a simple estimate using y bar. So this has some nice features, this estimate for mu y. Now let's consider again, towards the end of last period, we looked at estimating, getting expressions for these two things. And in terms of the population parameters, they can be expressed as follows. Okay, so you probably recognize the finite population correction here. And where do these come from? Formula 1 comes from a first order Taylor expansion of the function g of xy equal to y over x around the point mu sub x, mu sub y, and then squaring Formula 2 comes from a second order Taylor expansion of the same function. Okay, so we did a little bit of this last time. Let me briefly go through it. You have to compute the derivatives of g of x, y. The x derivative is minus y over x squared. The y derivative is 1 over x. Well, let me evaluate these derivatives at mu x, mu y, just to save a little time. The derivative of this in x will be minus y over x squared. Evaluated here, I get minus mu y over mu x squared. The first derivative in y of g, evaluated at mu x, mu y. Derivative of that with respect to y is 1 over x. Evaluated here, I get 1 over mu x. G xx, evaluated at mu x, mu y. The second derivative of that in x, the first derivative is minus y over x squared. The next derivative would be 2y over x cubed. 2y over x cubed. So here I get 2 mu y over mu x cubed. The mixed derivative at mu x, mu y. I differentiate first with respect to y, I get 1 over x. Then I differentiate with respect to x, I get minus 1 over x squared. So this would be minus 1 over mu x squared. And then finally, the second derivative in y is 0. And so g of x bar, y bar, these two characters should be near mu x and mu y. Remember, what's the variance of x bar? It's sigma x squared over n, and then times the population correction. So the variance is very small because you're dividing by the sample size. If the sample size is big, the variance is small. So that means this should be very close to mu x. Similarly, this should be very close to mu y. So a Taylor expansion around mu x, mu y should be valid for with very high probability. These will be with very high probability near mu x and mu y. So that's why this works. Now, gxx, I put that here. Well, let me write it out. I guess I should write out what the Taylor expansion looks like, and we'll substitute the values next. So this is a second order expansion. This would be R. This first term is R, right? This is mu y over mu x. What's mu y over mu x? Oops. R is mu y over mu x. So this first term here is R. Then we get, let me just write it as g sub x times x bar minus mu x. I don't care what this is because when I take the expected value, it'll vanish. That is, okay, and so plus what? This is 2y over x cubed, right? So multiplying by half, I get mu y over mu x cubed times x bar minus mu sub x squared. what was this? This is 0. And then this one was minus 1 over x squared. So here I get minus 1 over mu sub x squared, x bar minus mu x, y bar minus mu y. Okay. Okay, so if we just take, and what is this here? This is capital R, right? This function is this variable divided by that variable. That's capital R. So here's an expansion for capital R. Capital R is approximately equal to this. Since x bar is very close to mu sub x with high probability, y bar is very close to mu sub y with high probability, so R should be very close to this. So if we want to take the, if we want to expression for the expected value of R, we just take the expected value of the right-hand side. Now what happens when we take the expected value of the right-hand side? Expected value of R then is equal to approximately little r plus, now taking expected value here, we get 0 because expected value of this is 0. Expected value of that is 0. Here we get mu sub y over mu x cubed times, that would be the sigma x bar squared. That's the variance of x bar. Then we get minus 1 over mu sub x squared. And this would be sigma x bar y bar. Okay, but now we have finite population expressions for these things we've gotten before. Actually, we didn't prove this. We proved this, but if you follow the proof of that, this and substitute a y bar and this sigma x bar would be this thing. If you just modify the proof of this, you get this thing. Okay, and then this goes in here. This goes in here, and shake it all up, rearrange things. And you get this. Okay, that's where these terms come from. And for the variance of R, we just use the, so this is using the second order Taylor expansion and then taking expected value. To get the variance of R, we just use the first order expansion. Right, that R is approximately equal to, now G sub x, I'm just going to use the out to the first order. That means I'm going to stop here and use this one. Okay, so I should write down G sub x and G sub y now. Here's G sub x, here's G sub y. So I guess I need a minus sign here. Minus mu sub y over mu sub x squared. That's G sub x times x bar minus mu x. And then plus what? G sub y times y bar minus mu y. Now, how do you get the variance of capital R? You subtract little r, square it, and take expected value. So you subtract little r from both sides. And square. This will be about equal to this thing squared, which would be what? Mu y squared over mu x to the fourth times x bar minus mu sub x squared plus this thing squared. And then the product term. So it'd be minus 2 mu y over mu x cubed, x bar minus mu x, y bar minus mu y. Okay? So I subtracted little r from both sides and squared both sides. Now if I take expected value of both sides, again, x bar should be close to mu x, y bar close to mu y, so capital R should be close to the right-hand side, so these expected values should be about the same. And what's the expected value of this? That's sigma x bar squared plus 1 over mu sub x squared sigma y bar squared minus 2 mu y over mu sub x cubed, and this would be sigma x bar y bar. And now we substitute in these three things. This, and this, and here, here, and here, and rearrange, factor out stuff, you'll get this formula. Okay, so that explains where these come from. It's just Taylor expansions, and the basic idea is that the Taylor expansion should be good with very high probability when the sample taken is large enough, because x bar is concentrating near mu x. It's a random variable that doesn't vary too much from mu x, and y bar is concentrating near mu y. So that means these values should be close to each other. It means the Taylor expansion should be very close to being correct, to being the true value. The truncated Taylor expansion should be close. So, any question on that so far? All right, this is just calculus. All right. Maybe I'll put this up here. Try to save that one. And save these two. Let's see, do I need that? No. So we're going to try to get confidence intervals for little r. Okay, so let's think about how we got a confidence interval for mu in the mu sub x in the case of simple random sampling of a population. What did we do? We used use the fact that x bar minus mu over square root variance of x bar is nearly normal when the sample size is large enough and not too close to the population size. But the problem in using this to get confidence intervals was there's a sigma x squared in here that we don't know. So we had to estimate variance of x bar. And this was I think it was that, wasn't it? Or was it this one? Yeah. It was that. Or was it? It was, yeah, I had it right the first time, didn't I? Yeah. Where s little s squared was see, this depends on the sample. The s squared depends on the sample. And these numbers are known. So this is something you can compute once you've got the sample. And we use that for variance of x bar. So we have to do something like that here. It turns out the thing you use here is SR squared. Okay, so if you compare, variance of R has that finite population correction term in it. And so we keep that, and then we have to do what? Well, these are the real population parameters, and we don't know what they are, so we have to replace them by the things we estimate with them. So that's why we put it in here. Capital R squared, S of x squared, S of y squared. Okay. So how would you get a confidence interval for capital R? Well, this is, we won't prove this, but we use center limit theorem. So we'd have R plus or minus Z of alpha over 2, S sub R give endpoints of an approximate (100) minus alpha percent CI for the parameter little r. So with probability 1 minus alpha, little r is in this interval. And I think you remember the notation z of little alpha over 2? Okay, so this formally proceeds the same way as getting the confidence intervals from u sub x. Okay. And again, the variance of R has to be estimated by things you get from the sample. You can't put in the population parameters there, sigma x, sigma y, sigma xy, or R. So we put in the sample estimates of those things. Okay. All right, so that's pretty much like before. So let's go on to the second technique that uses ratios, and that's estimating, getting an estimate from uy using ratio estimates. So it reminds me, I put up a new link on the web page. How many of you have looked at the web page? Probably all, right? Because you have to get the homework. And the next Monday's homework will be posted this afternoon. How many of you looked at the videos? They're online. You can look at those. It's sort of a permanent record of my mistakes, which is the way I look at it. I also put up a link to web page, the Wikipedia web entry on Gossett. Has anybody looked at that? You might look at that. I just put one up for another statistician named Fisher, who's a very interesting guy. He also, Gossett communicated with Fisher. I'm saying this because I've just done a lot of technical stuff, and I can tell that you're getting a little overwhelmed, so I thought I'd take a little break. So Fisher also was very interested in genetics and evolution, and you might be able to track this down. He had an evolutionary argument for why the ratio of males to females in a population would be 50-50 if there was not incestuous if there wasn't incestuous reproduction. And turns out there's a very interesting insect, a particular mite, in which the male to female ratio is exactly 1 to 10. And this particular insect has incestuous reproduction. And here's the life cycle of this mite. This is an example to show why Fisher's argument might be is correct. This mite's life cycle begins with the female pregnant. She's born pregnant, actually. Attaches herself to a leaf. She has 10 infants in her womb, 1 male, 9 females, and this male fertilizes the eggs of all of his sisters. And in one variety, he dies before he's born, before he never exits the womb alive. In the second variety, he exits the womb and dies immediately afterwards. And so the females are born pregnant and they attach themselves to a leaf and eat. And this repeats itself. So in the cases where you have incestuous reproduction, the male-female ratio won't be 50-50, but in the other case, it will be 50-50. And Fisher gave a very interesting argument for why this works. Did you know about this mite? Anybody hear of this? You can read about it in Stephen Jay Gould. How would you like to be that mite? What an interesting life you have. Okay, so actually Fisher had many other very interesting ideas. One, I think, made everything we have now in the 20th century possible. Him and Shannon, I think, they had the idea about information. And in fact, it's even called Fisher information. All right. Meetings will resume. Let's do the second technique is to get estimates from UY by ratio estimates. Okay, so here we get that. So again, there's this sort of self-correcting effect here. If y bar is undersampling, then x bar in certain cases will be also. And so this would be bigger than 1, and that would increase the estimate. If y bar is oversampling, then in certain instances it would probably be true that x bar is as well. And so this would be less than 1, and this would correct it back down to value. So the variance of y bar R would be approximately what? Well, it's just mu x times the variance of R. I'm sorry, mu x squared times the variance of R. Well, it would be exactly equal to mu x squared times the variance of R. And that's there. So if we multiply that by mu x squared, it just knocks the mu x squared from the denominator. And so we get 1 over n, 1 over little n. 1 minus little n minus 1 over capital N minus 1. Is that R squared sigma x squared? Yes. Plus sigma y squared minus 2R sigma xy. Okay. And what about how far is the expected value of our estimator from the thing we're estimating? If it's 0, then this is an unbiased estimator of y sub mu sub y. So we're going to use y bar R to estimate mu y. this is on how far on average it'll be away from ui. And well, we have an estimate for the expected value of r. It's up there. If we divide this by if we multiplied through here by mu x, well, I'm sorry, if we multiplied through here by mu x, multiply this and this by mu x, what do you get when you multiply this by mu x? You get, right? Yeah, so if we get mu x r minus mu y, and then if we, that would be equal to this times mu x, right? Right? And that would be also that's our y sub r bar minus mu y, is it not? Or as they say in England, isn't it? Right? This is y bar over x bar. And if I multiply that by mu x, that's y sub r bar. Okay? So the expected value of this difference here would be this thing over here. I should say this is expected value. I forgot the expected values. So I just copy that thing over here. And it's minus, I think I have a plus. Like that. Okay, so it's an unbiased estimator, but if the sample size is big, and these things aren't too, this doesn't turn out to be too big, then it'll be not too biased, I would say. So let's take a break here, and then we'll look at estimating this thing after the break. There's no sigma y squared here. I copied that down incorrectly. There's no sigma y squared in the estimate for expected value of r. So there would be none here. Sorry, I made a misprint. So go back to the very first, one of the very first pages. I incorrectly wrote down plus sigma y squared here. It's not there. And that means it's not here either. Okay. Sorry about that. In these estimates, remember the square root of the variance of the estimator is called the standard error. And you want to make the standard error small. In other words, you want to have the variance be small. That means there's less, well, variability. So your estimator will be likely close to the thing it's estimating. So let's compare the standard error for y bar r and y bar. Well, over there, the standard error is the square root of the variance. So what do we get? I'll call them the standard error squared. Okay. Variance of y bar. And ignore the finite population correction. It'll be the same for both, so we'll just ignore that. And what do we get then? We get 1 over n r squared sigma x squared plus sigma y squared minus 2r sigma xy. And variance of r, variance of y bar is just sigma y squared over n. Ignoring, again, the finite population correction because it's the same for both. Okay. And that means, this means we should rewrite the first thing here if we want to compare them as sigma y squared over little n plus r squared sigma x squared minus 2r sigma xy over nothing, I guess. Did I forget something here? No. I forgot over mu sub x. Oh, right. Oh, that's right. Yeah. Over nothing, yeah. Over n, I guess. Okay. So when is the variance of y bar r smaller than the variance of y bar? Well, as you can see, that's when this term is negative, right? Or simplifying, that I am missing something here. There's a row here. If I write, no, this is correct. But let me write, remember what row is. I think I have it here. Here, it's sigma xy over sigma x sigma y. So let's substitute that in here. This is equal to that. So let's substitute sigma xy equal rho sigma x sigma y. Okay? And so I'm looking at the extreme sides here. This is less than that. That becomes R is less than 2 rho sigma y over sigma x. If I divide both sides by sigma x squared. Forget the middle part here. Divide both sides here by sigma x squared, you get this inequality. And I could leave it like that, but I'm not going to. I'm going to rewrite it as rho is bigger than 1/2 R sigma x over sigma y, right? And I'm going to rewrite that. I'm going to rewrite that right on the definition of R. Mu y over mu x. Little r is mu y over mu x. And if I do that, I can rewrite it this way. Put the mu x under the sigma x and the mu y under the sigma y. So you're good at these fraction manipulations by now. And so this numerator has a name. We'll label it C sub x and C sub y. So if rho is bigger than 1/2 Cx over Cy. This implies y bar r has smaller standard error than y bar. So it'd be a better estimator than y bar. These are called coefficients of variation. These are, this is how much the variable x varies. This is its mean. If the variance, if sigma x is 10, if sigma x is 10, but mu x is 10 million, would you say that's much variation compared to the value of mu x? Or maybe put another way, suppose your stock went up $1 a share. Would that make you a little happy, or very happy? Well, what if the stock was worth $1 million a share? You wouldn't notice it hardly, right? But if it was worth 10 cents a share, you notice a lot, right? So if this is the value of the stock and that's how much it's changing, you're more interested in this ratio than in how much it changes, right? You don't care about it. Like I often ask my kids, how big of a denominational bill would have to be on the ground before Bill Gates would bend over to pick it up? Would it be, at what stage would it be worth his time to, would he pick up $1? Or would he pick up $10? And why not? Because $1 compared to whatever his fortune is, billions, he might hurt his back. So these are more interesting in some sense than just the straight Okay, so let's look at an example. So this is kind of surprising that you have this sort of indirect way of estimating mu y that's better than sort of the direct way. By the indirect way, I mean using y bar r instead of using the direct way y bar. So there are actually these calculations in the text. Let me write down what the numbers are. I'll try to write down the correct numbers. Let's see. So I think this we don't need. So okay, so I is the hospital. We have two measurements for each hospital. One measurement is the number of beds in that hospital. The other measurement is the number of discharges in January of 1968 in that hospital. The true population parameters here for the example in the book are mu x equal 274.8, mu y equal to 814.6, sigma x equal to 213.2, sigma y equal to 589.7, r equal to 2.96, rho equal to 0.91. I computed Cx and Cy for these, and Cx would be 213.2 over 274.8, right? This divided by this. And that turns out to be 0.78. C sub y is this divided by, this divided by this, right? 589.7 divided by 814.6, and that's 0.72. So 1/2 Cx over Cy, which is the quantity here, is 1/2 of 1.08, or 0.54. And you can see rho is here. And rho is bigger than half Cx over Cy. So in this example, the estimate y bar r would have a smaller standard error than the estimate y bar for the number of discharges in January. Okay? So y bar r would be preferable. And in fact, you can compute these things, which I did. I'll do it over here, I guess. here sigma y bar r can actually be, if we, it's 1 for n equal to 9. I'm sorry, n equal to 64. So if we take a sample of size 64, remember that the population size here for this example is 393. Sigma y bar r, or the variance of y bar r, is 1 over square root of n. So that'd be 8 times s squared, s, which becomes 262.1, and then times the population correction, which is 1 minus 63 over 392, turns out to be 30, whereas the true variance is 29.9. So you see the variance for the estimator is very close to the true variance, whereas if you compute the variance for y bar, that's sigma y over root n times square root of 1 minus n minus 1 over capital N minus 1. Put sigma y from over there. Put 9 here, 64 here, here, and 393 here, and this becomes 66.3. So the variance here is more than twice that. So there's a big gain when you, I'm sorry, the standard error here is twice the standard error there. So there's a big gain in accuracy by using y bar r. Okay. So there will be some exercises based on the ratios. So there are two things, yeah.
There you have sigma y is 589.7. What do you mean by that one?
Well, here. Oh, this is not sigma y. That's s sub y. Remember s. That's from the sample. This is the true one. This is from the sample.
Yeah, I'm saying you have,
Here?
yeah.
Oh. Well, if I maybe these are the squares here. What's this? Wait, maybe this is. Oh, I'm sorry. These are squared terms here. Those things are squared. Sorry about that. Okay.
I don't think so.
You don't think so?
If you just took 30 and squared that, you got 900.
Oh, you're right. Yeah, you're right about that. Uh-oh. Let's see. Y bar. Oh, I see. I think y. Actual standard deviation of the 500 samples displayed. Oh, okay. So this is erase that. Okay, so forget about that. But the main point is this difference here. How much better this estimate is from that. So I'm sorry. Get rid of this. standard error here is much smaller, or at half the standard error there. Okay, thanks for pointing that out. Okay, now that's it for ratios. So again, there were two things we did with ratios. One is got an estimate for the ratio using, or confidence intervals for ratios using central limit theorem. And the other one was to estimate mu y using this ratio estimate y bar r here. And in the case where this is bigger than that, the standard error for this estimate was better than the standard error for using y bar. Okay. The next topic in Chapter 7 is called stratified sampling. And in this type of sampling, population is partitioned into subpopulations, maybe capital L subpopulations with capital N1, capital N2, capital NL members respectively. Where the sum of these numbers is capital N. That's the weight of the L subpopulation. So what are some examples? Maybe you're studying unemployment in the United States. You want some estimate of the number of unemployed, say females aged 30 to 40 in the US. Well, you could just take a random sample from the whole population and check the unemployment that way. Or you might divide the US into either states. L could be 50, capital L could be 50, and then you check the unemployment of women between 30 and 40 in each state, and then you make some combination of your sample and try to estimate the total unemployment figure for this group. Or L could be the number of regions. Maybe you would divide the US into regions like the West Coast, all the states west of the Rocky Mountains, maybe the Great Plains states, Southeast, Midwest, the Northeast. And then in that case, capital might be something like 5. And then you study unemployment figures in those regions, and then you combine them in some way. Okay, so let's look at the population parameters and measurements. So let's see. I want to know if I might have. I think I'm doing this right. xi1 No, I switched these. I should reverse these. 2, 1, and 1, 1. Okay, so the second number indicates the group number. So all these are in group 1. And this is the first individual in group 1, second individual in group 1, and one individual in group 1. Then down here I should do, similar thing. Group L, this would be the first individual, the measurement of the first individual in group L, the measurement of the second individual in group L, measurement of the last individual in group L. Okay. Okay, and then in each group we take the population parameters. Mu x1, I think, or is it mu 1x? No, I'll just call mu 1. I don't need to use the x. Mu 1 would be 1 over capital N1 sum I equal 1 to capital N1 xi1. The Lth mean, the mean in the Lth group would be 1 over the number of elements in that group, and then just the sum of the numbers you see in that group, etc. And similarly, sigma 1 squared would be 1 over n1 sum I equal 1 to capital N1 xi1 minus mu 1 squared. Sigma sub little l squared would be 1 over capital NL sum I equal 1 to capital N sub little l xi little l minus mu l squared, etc., down to sigma l squared equal to 1 over capital NL, capital N capital L, I equal 1 to capital L, xi capital L minus mu capital L squared. Okay, so we form the mean and variance in each group separately. the total mean could be written this way. This sums all the possible population values and then divides by the population size. Now this thing inside here is what? If I look at this term here, that circled term is what you see here. Right? The thing in the circle is what you see here. So this would be equal to capital NL times mu L. Right, just solving that equation there for the term in the circle. And then I can rewrite this as the sum L equal 1 to capital N by pulling the capital N inside and recalling that I'm calling capital NL over capital N the weight of the Lth class. I get mu sub L times the weight of the Lth class. So the whole average is the sum of the weighted averages of the individual populations, weighted by the population size, subpopulation size. So for example, if you split the US into state by states, the weight of California, which would be little l equal 1, right? Being the first state, or the best state, would be about 1 in what? I think it's 1 in 8. Weight of California would be 1/8. 1 in 8 people in the United States is from California. But the weight of North Dakota would be almost 0, because I think there are more people in, if you combine Huntington Beach, Irvine, and Newport Beach, there are more people there than in North Dakota. So it makes sense to weight subpopulations that are bigger with more weight than subpopulations that are smaller, because the unemployment figures in North Dakota won't have much influence on the, if you're thinking about the whole country.
How does the L and the double sum to the left become N?
Here?
To the right, in the next step?
Here.
You have,
Okay.
No, I see that part, but I'm saying you have the sum going from 1 to capital N.
Oh, I'm sorry. Yeah. That's capital L there. Thanks, capital L. Okay. And it's mu that we want to estimate. And we want, if possible, to stratify the population to in a way that minimizes the standard error of the estimate. stratify the population and select a sample. So maybe I should add that in here. Stratify the population and select a sample. In a way that minimizes standard error. But actually, maybe I should be more careful. Let me reword this. What, if possible, given a stratification, to select a random sample, simple random sample, in a way that minimizes standard error of the estimate. Okay, so what we're going to do is sample each strata independently. Selecting little n sub l individuals from the capital N sub l individuals in the Lth strata to note the resulting random variables by x 1L, x 2L, up to x n sub little l, L. Okay, see we have little n sub l observations by this random selection, and assume the sets of random variables Okay, so that means this set of random variables is independent of this set, is independent of this set, is independent of this set. It doesn't mean that the random variables in each set are independent. These are dependent. These are a simple random sample from the first subgroup or strata. This is a simple random sample from the second strata. So in each set, the random variables are weakly dependent if the sample size is big enough. Remember, the covariance would be minus sigma squared over the sample size minus 1. Or sorry, the population size minus 1. Population size would be the capital N numbers. But from one set to the next, they're independent. So in other words, we sample here, we forget what we did. That doesn't affect how we sample the second strata, doesn't affect how we sample the third strata. So from strata to strata, the samples are independent. Okay. So what's our estimator for mu. Ta-da, ta-da. Let's see, what can I use here? I guess I'll... Okay, drum roll, please. X bar S. I guess I call it X bar L. Where X bar L so each one of these would be an estimator for mu L, right? This is an unbiased estimator for mu L. Okay, that's just a separate population, that little elf population. We take a random sample of that. Its mean is mu sub L. What's the unbiased estimator for mu sub L? Just the sample mean, sample average, right? Okay. So the expected value of X bar L is mu L, right? Expected value X bar L is mu L. So if I take the expected value here, I take the expected value of this sum, I exchange sum and expected values. The WL is a constant, that's a number. So I take the expected value of this. What's the expected value of that? Mu L. So expected value of XS bar would be the sum mu L WL. And the sum mu L WL is mu. So it's very simple that this gives an unbiased estimator. So you just take sample averages in each substrata, in each strata, I should say. Each subpopulation is a strata. Take sample averages in each strata, weight them according to the proportion of the individuals in the total population in that strata, and that gives you an unbiased estimator for the total mean. Okay? Okay, now using the independence from set to set, we can get an expression for the variance of X bar S. Now these sets are independent. So what about the random variables X bar 1 through X bar L? This is formed from random variables in the first set. This is formed from random variables in the second set. This is formed from random variables in the Lth set. Those sets are independent, so these random variables will be independent. And here what do we have? These are numbers, fixed numbers times these random variables. The random variables in this sum, this is then a random variable. The random variables in this sum are independent from each other. The lth one is independent of the kth one when L is different from k. So here we have a sum of independent random variables, and we're taking the variance of that. What's the variance of a sum of independent random variables? It's the sum of the variances, right? Now reverse the order here. We have a multiple of x bar L. So that's here. And I can pull out a WL squared. And here we have the variance of a sample mean. And using simple random sampling, we know what that is from earlier in this chapter. It's that, where sigma L squared, I think I wrote it down, didn't I? I erased it. This would be the variance of the Lth subpopulation. Okay, this is just the finite mean correction, finite population correction that we talked about before. Okay, so that's the variance of our estimate. Okay, so next time, well, I'm sorry, this should be little nl here and little nl there. Okay. Next time we'll see how we can pick little nl to make this small. Has anybody here taken a course where they talked about Lagrange multipliers? This is a function of capital L variables, n1 through little n1 through little nl. And you just take the gradient in that. And there's a constraint. The constraint will be that the sum of the n sub l's will be some number little n. And you want to minimize this subject to a constraint. It's a very simple computation.